My name is Bill Van Buskirk, and on behalf of the Committee on the Technology and Society Forum Series, I'd like to welcome you to the latest installment of this series. I've been asked to encourage you to turn off your cell phones and to note that Blackberries, even in their silent mode, will disturb the wireless system here. But I'll leave it to your conscience. We're delighted to have with us today Chris Phoenix, who is the Director of Research of the Center for Responsible Nanotechnology, an organization of which he is the co-founder. Chris's education was at Stanford University, and he has been engaged in nanotechnology research, study, writing for some 15 years now. We're delighted to hear from Chris, who will speak on the subject of molecular manufacturing, productive nanosystems, and digital nanomedicine. Chris?
Thank you. Okay, nanotechnology is a huge field, and I'm going to be talking about one tiny little part of it. But it is, I think, the most important part. Most of nanotechnology that is done today, what I call nanoscale technologies, things like nanoparticles, carbon nanotubes, better computers, are usually incremental improvements over the way that things are done today. Stronger materials, better computers. Molecular manufacturing will be a step as big as the invention of computers in the first place, as big as the Industrial Revolution. So the first thing I'm going to do today is explain the physical basis behind that rather extraordinary claim. I'm going to talk about the effects that molecular manufacturing could have, the implications, both good and bad. And I'm going to spend a fair amount of time on health as one of those effects, health and medical advances. And then I'm going to go into more detail on the effects, depending on how much time I have left. Okay, start by imagining a very prosaic piece of technology. It moves up and down, and it adds thread to cloth and fastens things together. Over here, we have this is taken from a simulation. And if you picture this as a sewing machine needle that's going to come down and make a change to the chemistry of this molecule down here, and then this is a second one that's going to come down and make a similar change. I'm not going to run that simulation. You'll see a more integrated version of such things later on in the talk. But the idea here is this is mechanical, and each piece of it is fairly simple. So direct mechanical control of chemistry. Ribosomes in cells have direct control of the proteins that they make, and they're programmed by DNA. In molecular manufacturing, we would use somewhat different types of chemistry, more like the ones that I showed you in the previous slide than like enzymes, but still pretty much related. An advantage of molecular manufacturing of working at the nanoscale is that small things move faster. So where today's scanning probe microscopes could move maybe 1 atom per second, when you shrink them by a factor of 1,000,000, they could move maybe 1,000,000 atoms per second. So that starts to add up pretty fast. Even though atoms are amazingly small, when you move 1,000,000 per second, you can build a 1,000,000,000 atom construct in about an hour. Working with atoms is very precise and reliable. Molecules have a specific shape, and each molecule of the same structure has an identical shape. Now, just for a comparison of what you can build out of blocky things, we have here a machine which grabs a Rubik's Cube, looks at it, rotates it, spins it around, and solves it under control of an appropriately programmed external computer. Now, one difference is that there's no cameras at the nanoscale. Light is too big. But in terms of the physical manipulation, you could imagine this as a molecule and these as more molecules, and each block as an atom or a small molecular fragment strongly bonded together. Here we have a system. This has actually been built by Nadrian Seaman. These are DNA strands, and this is a very clever machine. It's built out of DNA. It's programmed by DNA. These little things that look like hairs are DNA strands that you add, and this component rotates, just as the arms rotated in the previous slide. And it's not only built out of DNA and programmed by adding DNA strands, its purpose is to build DNA strands. So a strand attaches across the top, and you build a certain sequence of the strand. Now, if this were rotated so that the 3 and 5 were highest, then it would build a different sequence. So this is not yet molecular manufacturing, but it's starting to point the way. A machine that can build molecules of the same class as itself, although not yet the same physical complexity. Productive nanosystems is the class of machines that are built out of atoms and can build things out of atoms. It goes beyond nanomanufacturing. The idea is not only to build small stuff, which of course has the advantages of scaling laws and precision, but to use small tools, which has the advantage of high throughput and scalability. Digital control is very important. You can build simple things at the nanoscale today. You can build nanoparticles, you can build small constructs out of DNA, but if you want to build products like intricate medical devices, you're going to have to put gigabytes of information down to the nanoscale. The only way to do that, I think, is with nanoscale actuators. And so productive nanosystems is about bringing nanoscale actuators to the nanoscale. Digital control also lets you minimize errors. If you have an analog process, then you're always approximately right, but you're never precisely right. With a digital process, it's the other way around. You're either broken or you're exactly right. And so if you can tweak the engineering so that you're usually exactly right, then you can work with remarkably little feedback. I think they call that open loop control. You can maximize the control over what you can build if your manipulation system is computer controlled, then simply changing the blueprint changes the product. And that has some implications for rapid design. As I said, molecules are precise. Another thing about molecules is they have excellent material properties. Metal, if you bend it, it'll deform like plastic. Covalent molecules are quite a bit stronger than that. Plastic is a bunch of molecules loosely attached. But if you can make single molecules like a Bucky tube, they can be far stronger than any construction material in use today. Okay, exponential manufacturing is one of the key benefits of molecular manufacturing. If you have a small manufacturing system that can fabricate its own weight in a minute, more or less, maybe an hour, and even if it's as much as a day, it's still pretty useful. You can use that to build another manufacturing system, run them side by side to build 2 more, and in a fairly short time, about 60 doublings, you can get from a 100 nanometer basic system up to a kilogram scale manufacturing system. So, and that would make about 1 kilogram per hour. This kind of scale up is not contemplated in any other field of nanotechnology, except possibly engineered bacteria, but there you have all sorts of control problems. You can make, as I said, integrated manufacturing systems with lots of workstations all fastened down. That's easy to control, easy to get information and materials to, and easy to know where the products are ending up. If you make lots of small systems, then you can only use them to make small products, but if a small system breaks, you can throw it away. So you may actually not need any error handling if your error rate is small enough to build a small system on average without an error. You can increase the number of systems each generation even if you have to throw away a fraction of them because they're broken. Now, one of the big problems, I should have said, with engineering at the nanoscale is seeing what you're doing. If you can build a process that's sufficiently automated and reliable, perhaps you don't need to see as much of what you're doing. In research, you need to see it to design the thing in the first place, but when you're actually running, you can run it fast and deterministic, and not have to have feedback all the way back up to the macro scale to check on what it's doing. Okay, I talked about this already. With a 100 nanometer robot, it moves 1,000,000 times as fast. It's 1/1,000,000th the linear size, which means it's 1/quintillionth the volume, which means that the throughput scales as the 24th power, which is how you can have something building one atom or one molecule at a time that can process its own mass in 100 seconds. Not only the factories, but the products can work very quickly. As I said, covalent solids, bucky tubes, can be 100 times as strong as steel. You can build very, very intricate construction because one of the things you can build is nanoscale computers integrated with the manufacturing system. That lets you decompress the information in the same way as a PostScript file sent to the laser printer is much smaller than the binary pattern of dots on the page. But if you have interesting, useful patterns, you can send them and have them decompressed at the local scale. That's another way of getting a lot of information and intricacy into your construction. Because of the material properties and even more so the scaling laws for motors and computers, you have to manufacture vastly less mass than you do with today's products. 10,000 watts per cubic millimeter seems like a reasonable value for motors. It would be difficult to cool, but if you spread that cubic millimeter over a wide area, you could probably do it. And what this means is in any human scale product, the volume of actuators is going to be trivial, which eases your design somewhat. Power transmission, mechanical power transmission scales similarly. The NEC Earth simulator, until recently the fastest supercomputer in the world, could be built in a grain of sand and run on 2 watts. Chemical processing, I'm not going to get into a lot today. The Nano Factory level that I'm talking about is a fairly early one, and it will mainly make strong, rigid covalent solids. For other chemical processing, you might need to develop other sewing needles or knitting needles or whatever. You might build microfluidic things and do your chemistry wet like it's done today. So there are a lot of options there. Some of you may be feeling skeptical. Well, Richard Feynman said back in 1959 that atomic scale machines could be built. He did not propose exactly the same way that we're talking here, but the basic idea of atomic scale machines, Feynman was cool with that. A lot of preliminary engineering has been done. There's been a 500-page book written that's chock full of formulas. I've written about an 80-page paper on some of the Nano Factory engineering. Doing chemistry with needle-like probes has been demonstrated actually for a fair number of different chemical reactions. And a lot of the objections that I've heard over the years are not actually related to the proposals. There have been issues that came up as we looked deeper into the design, but so far they have all been relatively straightforward to solve, and conversely, some things that we thought would be difficult have turned out to be relatively easy. At this point, I want to show an animation of a movie, of a Nano Factory, and this will show not all the detail, but it will show some concept of the scale up from doing chemistry all the way up to products you can hold in your hand. And the chemical reactions that it shows have been simulated at a fairly high level of theory.
From molecules to super products. Final production made possible by a challenge grant from Mark Sims and Nanorex Incorporated. Future advances in molecular nanotechnology will enable desktop appliances to manufacture products far better than today's best. The cartridges to the left supply simple raw materials to the machinery inside, here shown in schematic form. Products emerge from the top of this box, which holds the heart of the manufacturing system. Each product is built from beneath, layer by billions of tiny machines, all working together. Near the top surface is the productive machinery itself, organized into layers. Machines in the lowest layer process molecules into building blocks, passing them upward to machines that assemble them into larger components, and then to machines that add these components to the product. From a millimeter scale, 1 million nanometers, our view zooms in to the 10 nanometer scale. Each box is 1/10 the size of the one before. Here, at the molecular scale, Nano Machines make small building blocks from molecular raw materials. The first machines sort molecules by their size and shape, passing some, rejecting others. Only molecules of the right kind can enter the processing machinery. These molecules contain 4 atoms, 2 of carbon and 2 of hydrogen. The molecules bind to a device that carries them to the next stage. Then, a rotating mechanism swings tool tips into contact with the bound molecules. Each tip presses a molecular tool against a molecule, bonding it firmly. The tools shown here have been analyzed using advanced quantum chemistry techniques. Another tool moves in from the left to remove the hydrogen atoms, leaving a pair of carbon atoms exposed and ready to use. The tools then carry these atoms to their destination, where each pair bonds to a nanoscale building block, making a tiny bit of crystalline carbon, a bit of diamond. Motions happen quickly at this scale. This scene shows motion slowed by a factor of more than 1,000,000. A conveyor carries the blocks past further machines, which build the blocks step by step to full size. Elsewhere, other specialized machines build blocks of different kinds. A system of conveyor belts and transfer mechanisms carries completed blocks from where they are made to where they are needed. This transfer mechanism moves blocks from one belt to another. The transportation system carries many different kinds of blocks, different shapes, different materials, different functions. It delivers them to the next stage of manufacturing. Here, a programmable machine lifts and places small blocks to make larger blocks. The small blocks bond on contact to form components containing millions of precisely arranged atoms. These can be simple structural bricks or intricate components for mechanical and electronic systems. The completed components are delivered to the final assembly stage, where many machines work together to build the final product. Motions at this larger scale are still quick. This scene shows motion slowed by a factor of 10,000. At the base of each machine, a transfer mechanism grabs components and lifts them from a conveyor. Each is flipped around, then carried up to the underside of the product under construction. Finally, machines lift the components and plug them in place, adding layer after layer to the bottom of the product. When the last layer is finished and construction is complete, the product is ready to be removed and used. The result of this production run is an atomically precise multiprocessor laptop computer with 1,000,000,000 times more processing power than today's best. The only waste products are warm air and pure water.
Okay, when could we have that? Soon. We can now do top-down nanoconstruction, things like lithography, making smaller feature sizes than the molecules that we can build. Molecular manufacturing is increasingly becoming a topic of interest worldwide, probably more so in other nations than in the US. I've thought for a while that a Manhattan project might do it in as little as 5 years. And as time goes on, I probably won't reduce the time estimate because software has to be written and that always takes time. but I'll reduce the cost estimate. Today it might cost several billions or even as much as $10 billion. 5 years from now, it would probably cost a couple $100 million. 10 years from now, it might be done in a well-equipped university lab. Okay, the big question with the development of it, with the schedule, and also where it'll be developed is who wants it? Not who can do it, but who tries for it first. This we do not know. Now, once you have a nano factory, how do you build the products? Well, you design them, but the key is you design them the same way you design software, because you go direct from blueprint to product in a time that's not too much longer than the time to compile a program. Because the active components of the product will be so ridiculously small in comparison, as I said, with any human scale product, you have a lot more room to keep the product simple. You don't have to leave as much room for ducts and wires and motors. There will be a huge range of products that can be built, even with just diamondoid materials, diamond, bucky tubes, graphite, things like that. Basically, most of the things you see in this room, aside from the food over there, and of course the people, could be built with this technology. Okay, I'm running a little behind, so I'm going to accelerate a bit. But as the movie said, the elements in use are basically carbon and a few other things from near the top of the periodic table. That should reduce the mining and processing of minerals. The value per cost is extremely high, especially since, notice that a nano factory, there's nothing to prevent it from building another nano factory. We haven't had non-scarce manufacturing systems yet, but that should drive down product cost quite a bit. Let me talk a little bit about nanobots, because we're starting to get into the implications. A nanofactory is not a nanobot. A nanobot is more or less a science fictional concept that the definition depends on the author that's using it. One thing a nanobot is not is an assembler. An assembler is a very small, self-contained nanofactory. Back before it was realized that you could take the shell off and put a lot of assemblers together in ranks in one nanofactory, as you saw in the movie, the original concept was assemblers. And so people got the idea that all products of assemblers would include assemblers, and thus the nanobots would be able to build stuff whenever they wanted to, and this was a little spooky. Now, I did a Google Images search on nanotechnology, and this is what I came up with. It's no wonder people are a little bit nervous about it. This one over here actually is one of the better ones. It looks more like a sea creature than like an insect. But the field of nanotech, I think, has been damaged by its association with insects. Okay, implications. Computers become vastly cheaper. This computer that I'm using here, 10 years ago would have not been purchasable. I bought it for under $1,000. If you can build computers with fully automated manufacturing systems where the systems themselves are not scarce and the materials themselves are inexpensive, something with the power of this computer would fit into one of the buttons on my wristwatch. No, one of the bacteria on one of the buttons on my wristwatch, and would cost a very small fraction of a penny. This has advantages in a couple of things we all approve of. Spaceflight becomes affordable when you have cheaper construction and much better materials. Medical advances, I'll be talking a lot about that later. More positive effects, rapid infrastructure development, and also more local manufacturing, greater self-sufficiency. When you can do efficient manufacturing without so many raw materials, so much transportation, so much waste, then you can have a lot lighter footprint on the environment. Also cleaner energy sources. And when you have essentially unlimited manufacturing capacity, you can do planet scale engineering. It becomes actually reasonable to talk about pulling CO2 out of the atmosphere on a planet-wide scale. Negative effects, of course, any technology this powerful will have them. I'll be talking about these later on, but I want to mention one right now, which is war. Rapid R&D of amazingly powerful products followed by unlimited manufacturing sounds to me like a great recipe for an unstable arms race. For about 6 or 8 reasons, this looks a lot less stable than the nuclear arms race was, which almost had a nuclear explosion at several different times, sometimes by accident, sometimes by design. So if we get into an arms race with this technology, I am not at all sure that we'll get out of it. I do not know how to avoid it. This is a serious problem, and I don't know how to say it pessimistically enough. There is no known solution to keep us out of an arms race that would lead to devastating war. I'll come back to the implications, but for now I want to talk about the medical implication because I'm told there's a lot of medical people in the audience. Let me take a poll. Who here is into medicine, nanotech medicine? Okay, very good. We already see trends in medicine today where I'm not saying today's medicine is butchery, but it used to be, and today we have surgery. Pain has become a lot less, but there are still things like cancer that can cause intractable pain. Waiting, anyone who's tried to use an HMO knows that that is still a condition today. We're moving from hands to gadgets, and we're moving in understanding from causes to systems. I want to read not this whole thing, but cured is a finite state, not a process. It involves separation of the disease or disturbance from the person. You don't heal, conversely, from something you're afraid of. You heal towards something you deeply desire. Healing involves a very personal medicine. Where I'm going with this is today, medical cures are one size fits all. Almost everything you use in a doctor's office or in a pharmacy has been approved through a process of clinical trials where you are given a statistical guarantee that it is very likely to work on you because, hey, it works on a large fraction of everyone else. This is how medicine is done today. It's not a bad way, but when we have the ability to match cures to your particular genome, which they're already talking about. I was at a Future Medicine conference last week, and they're already talking about looking at your individual genetics and matching a cure to that. When we have the ability perhaps to even rapid prototype the curative devices and eventually the curative molecules, and when we have the ability to plan surgery at a much more detailed level than today, it'll be possible to, rather than just trying to prod your body away from disease and back to health, it'll be possible to maintain you at an optimal or even super optimal state of health for you. Tomorrow's medicine will have new drug families, for example, buckyball-based drugs. In some decorations, buckyballs are toxic, but in other decorations, they can be quite useful. We can have lab-on-a-chip for more rapid diagnostics, nanoparticles for improved sensing. We have a human genome, but we don't yet have a human proteome. That's coming. That's the understanding of what proteins are expressed. We have elegant surgery, robotic surgery, for example, on eyes, where the robot can keep track of the movement of the eye and move the knife as your eye wiggles so that it cuts straight. No human could do that. We're going toward automated integrated medicine. Implantable devices are getting better. That implies implantable sensors. Today, most information that the doctor has about you is a snapshot. You come into the office, he takes your blood pressure. Well, fine, what was it an hour ago? What was your average blood pressure over the past 24 hours? No one knows. We will. What was your blood sugar level over the past 24 hours? What was your stress hormone level? All of these things will be achievable through convenient sensors, either implanted or worn, This will allow a system-level approach. This will allow performance tweaking. As I said, not just keeping you away from the worst of disease, but moving you toward, okay, your stress hormone is 5% too high. What can we do about that? Finally, aggressive R&D. My claim is that if you can monitor the body in detail, and if you have a good enough computer processing ability, then you have diagnosis. If you can data mine, say, 10,000 indicators, which is not beyond possibility with an RNA expression chip, if you can data mine 10,000 indicators of the body's state, then you can probably diagnose it in real time. Now, real-time diagnosis implies that you can tell, usually very quickly, what your treatment is doing to that individual body, whether it's your own body or the body that you're treating. That implies that you can be simultaneously much more aggressive and much safer in your treatments. You may even be able to do experimental R&D as a normal process of curing disease conditions. Someone walks in, well, I don't know if this will work, let's try it. 5 minutes later, well, that didn't work, let's try something else. Whoops, let's counteract that and try something. Oh, okay, that works, great, you're cured. 15 minutes for what today would take a massive medical research project. Okay, so far I've been talking about things that we will have in current medical trends. What can you do when you have a Nano Factory in the mix, building devices smaller than a cell? Well, today we have, as I said, nanotech is largely incremental over things that we can do anyway. Molecular manufacturing, molecular nanotechnology sounds like science fiction. I somehow forgot to put in a quote here that I always like to start my talks with from Christine Peterson, co-founder of the Foresight Institute. If you're trying to predict the future and your prediction sounds like science fiction, it could be wrong. But if it doesn't sound like science fiction, it's definitely wrong. So some of the devices that have been proposed are a submarine that cleans your arteries, a respirocyte, which is a compressed gas tanker on a micron scale, clotocyte, which makes your blood clot more quickly, microbivore, which vacuums up unwanted biologicals in your bloodstream, and finally, I'll touch briefly on vasculoid, which is something I co-invented. Actually, I want to talk about that. One final really aggressive nanomedicine concept is Hetero Stasis. The body is very good at homeostasis, keeping a bunch of parts working basically on an even keel. The idea of Hetero Stasis is when aggressive treatment is needed, you separate the parts and provide each part with enough life support that it can work independently. Not too long after I developed this concept, there was a treatment done where someone had cancer of the liver, and the liver needed too much radiation to deliver through the rest of the body. So they removed the liver, carried it to a particle accelerator, irradiated it, and then put it back. Now, this is science fiction, except that it actually happened a couple of years ago. And last I heard, the patient survived and the cure was successful. So maintaining that liver alive would be a very primitive example of heterostasis. Eventually, it may even be the case that heterostasis is useful for maintaining superoptimal health. For example, if biologically you're most healthy with a 10-year-old heart and 20-year-old bones, there may be no way to do that in an integrated system. But if you can make your heart see 10-year-old hormones and your bones see 20-year-old hormones, then you may be able to be actually healthier than anyone could be today. Okay, artery scrubber submarine. The main point of this slide is artists' conceptions are usually wrong, and many of the proposals for nanomedicine are just artists' conceptions, and nanomedicine will not be easy. For one thing, the stakes are very high. For another thing, many of the devices are small enough that you don't get the simplicity advantage of being able to shrink your things ridiculously small in comparison to the device. The respirocyte is a relatively simple device. It's basically just a gas tanker and some pumps, molecular pumps, with materials far better than biology. You can store gas at 1,000 atmospheres, and a maximum therapeutic dose thus lets you go 3.8 hours without breathing if you're sitting still. Very convenient, especially in trauma cases. The claudicide I already mentioned. Now the vasculoid at the other end of the spectrum, this is an incredibly complex device which very likely will never be built. The idea is to replace the fluid in your blood with mechanical transport systems. So line the blood vessel with a jointed robotic device which transports tankers and cellular boxcars to do all of the transport and regulatory functions of blood. Now this of course has some advantages. It of course is extremely difficult to do, and it's likely that we'll all be putting our brains in vats before we ever develop a vasculoid, but it's fun. And I co-authored with Robert Freitas, author of Nanomedicine, co-authored about a 120-page paper to bring this from the artist's conception to, oh yeah, I guess I can see how that might work with a whole lot more R&D. As I said, it does have some benefits. I'll skip these, except to point out direct spatial control of biochemistry. You can maintain different levels of chemicals at different parts in the body. You don't have the bloodstream mixing them all around. So again, you can deliver different hormones to different parts of the body. Okay, that's it for medicine. Back to concerns in more detail, and I want to leave time for questions, so I'll go through these very quickly. Standard concerns about nanotech that I've seen in science writing over the past few years. Nanobots will eat people, nanoparticles will poison people, et cetera, et cetera. Notice that these are all fears about what unknown technology can do to people. These are not technology-based fears. Nanoparticles are starting to be technology-based, and we're starting to find that they actually do, some nanoparticles do have health and environmental concerns. I don't mean to make light of those, but the idea that all nanoparticles are spooky and therefore bad is one that we could do without. Here are some of the reasons why we should actually worry about nanoparticles. A couple of years ago, people were pretty clueless. We're starting to get some clues now. I say we. CRN doesn't focus on nanoparticles. We direct inquiries to CBEN at Rice. Okay, social and ethical concerns. Again, this is what I'm seeing in more or less the mainstream talking about nanotech in general, not molecular manufacturing. Businesses are very afraid that it'll turn into another genetically modified organism fiasco, where a public outcry will kill the business. Fear and distrust. Businesses fear what they call pressure groups, and NGOs fear rampant capitalism. There is, so far, a lack of knowledge and a lack of regulation and a lack of understanding of how much to regulate. Okay, I should talk about gray goo because that was one of the big early concerns specific to molecular manufacturing. The concern is if you have a small self-contained manufacturing system, what if it decides to not turn itself off? Well, first of all, it would be very difficult to build a free-range manufacturing system. It would be like the difference between a laser printer and a laser printer that could go out to the supply cabinet and get more toner when it ran out. Actually, it would be a lot worse than that. It would, well, anyway. The second reason why I'm not so worried about gray goo as people were worried 2 decades ago is modern manufacturing systems are not small and self-contained. They're large and programmed externally and fed with feedstock. So there's nothing like a gray goo bot. There is no self-contained module within those manufacturing systems. If you broke one apart, the air would go in and corrode it in a fraction of a second. Okay, so threats from molecular manufacturing. Nanofactories don't exist yet. The threat right now is confusion. People talk about gray goo. Other people say, oh, the whole thing is impossible. This is improving over the past couple of years, but CRN has spent the last 3 years trying to deal with that confusion. As the possibility becomes accepted of nanofactories, there could be extreme reactions. There could be, instead of 1 Manhattan project, there could be 5. They might finish within 3 months of each other. That's a great recipe for an arms race. Eventually, we'll have destabilizing technologies. For example, that speck of dust might be a spy bot. Things like that. That mosquito might actually be a lethal weapon. Darn it, I'm not supposed to talk about insects. That hummingbird might be a lethal weapon. And possibly the very high-powered technology would open the door to a tech-based runaway, Skynet. Timeline depends on who you ask. Could be, okay, this is actually, I admit I copied in a slide from a talk that was a couple years ago. 10 years from today is actually now reasonably well supported. I'm not saying it will happen, but it's very plausible that it could. So I would say 5 years to never, and the 5-year extreme is not well supported. I think within 10 years, a number of companies would be able to build a nano factory within their budget, within their planning horizon, and if the military hasn't done it by then, some company will do it. Okay, this is almost obvious. Molecular manufacturing could both mitigate and cause a lot of problems. What should we be doing? We should be figuring out the timeline and the impacts. We should be hearing from all the stakeholders. We should be casting the net very wide for solutions. We should be learning to create balanced policy. What are we doing? We're ignoring it. We're pretending molecular manufacturing doesn't exist. Until recently, the National Nanotechnology Initiative was actively opposed to the possibility of molecular manufacturing existing. The only thing they said on their website was that nanobots were dangerous, science-fictional creatures. They've changed that now, but for a while they were saying that. Okay, lots of interconnected problems. But this is a vicious cycle. Okay. I see some of you are awake. Thank you. There are lots of things that could feed back on each other. Oppression leads to violence, black markets, and unhappiness. Various other risks. I'm going to try to leave time for questions because I know some of you have exams. How many of you have to leave for the exams? Yeah. All right. So one question is, when manufacturing goes away, what will all the manufacturing people do? I understand there's some previews of that in the American auto companies today. I'll leave you with the thought that a century ago, something like 30 or 40% of Americans were farmers. Now it's 3%. What happens if 10 or 20 years from now, 3% of Americans work in manufacturing? This last one is really interesting. Can every nation police itself? Well, obviously not. There are lots of nations that can't police themselves. Can nations police each other? I would argue no. Nations can occupy each other, but they can't police each other. A police force can't be that separated from the people it's policing. It turns into an occupation. So we either have a lot of occupied nations or we have a lot of lawless nations. And if you have a portable nano factory, if you have a box sitting on this desk that could make a sufficient quantity of weapons to kill 1 million people, how do you square that with a world in which nations are unpoliced? And if you go for the occupation route, how do you avoid a dictatorship that's utterly unbreakable and unaccountable when that dictatorship has this much power and doesn't allow anyone else to have it at all? Okay, the world has a few systems today, and I can't do this slide justice, but we have a paper on it called 3 Systems of Action on our website that I encourage you to look at. One type of system deals with negative sum events, trying to prevent them from happening. This is the feudal or police or military system. The markets are for dealing with positive sum events, where you try to maximize the number of those events and maximize the efficiency around them. And obviously, it has a very different set of style. There's a third kind of system that has come into being since networked computers made bits too cheap to meter. That's unlimited sum systems, where the cost to, for example, copy a data file is very much smaller than the benefit and unrelated from the benefit. It's not infinite sum, but it is unlimited sum. If I give you my aunt's cookie recipe, there's no telling how many good cookies will be baked from that. And again, it has a third, very different set of ways of dealing with the problems that it faces. These three systems probably cannot be combined into one organization. They have to learn to live with each other. Just as if you try to combine commercial and military in one nation, you get either Nazism or communism. If you try to do it in a private organization, you get the mafia. So we're going to have to deal with not only the traditional guardian and commercial systems, we're going to have to deal with unlimited sum systems. Nanofactories, making nanofactories allows effectively unlimited amounts of production and unlimited value from that production. We don't have any system today that can deal with it. Not markets, not military. No system in existence today can deal with it. Even open source can't deal with it alone because it brings in lots of security issues and lots of commercial issues. Okay, I've identified 10 impacts here, 10 areas of impact for molecular manufacturing. Each of these deserves a book. I'll give it a slide. And there's a lot of work to be done to understand these. Going back to the vicious cycle thing, I would claim that we have to understand these at least somewhat, understand their interactions, which is, 10 squared. It's a lot of interactions to understand before molecular manufacturing comes along. Okay, molecular manufacturing could become the dominant manufacturing system within months. It wouldn't replace every product overnight, but it could replace a lot of the highest value products very quickly, including energy infrastructures, computational infrastructures, and probably pretty soon transportation infrastructures as well. Cheap solar power, this goes to the environmental remediation, and inconceivably cheap computers, as I said. High-performance avionics. Space access will become approximately as easy as airline access is today. Environmental issues. Manufacturing gets a lot more efficient. The Earth has a carrying capacity of at least 100 billion people, more than 10 times today's population, if this technology is used well. Okay, obviously, if this technology is not used well, then it allows a level of profligacy where 1 million people could, use up all of the environment's resources. So we have choices to make. The ultimate limit on the planet is heat pollution. You can't get rid of heat except by radiating it away to space. That's a slow process. We may be able to use only about, 100 times the energy that we're using today. Even if we generated no carbon dioxide, even if we took carbon dioxide out of the atmosphere, the Earth would still have limits in how fast it could radiate away that energy. Okay, lots of things become less costly. The physical handling of goods and the physical manufacture of goods become less costly. Keep in mind, nanofactories can be small, local, and just in time. So you don't have to warehouse, you don't have to transport as much, in addition to manufacturing itself being more efficient. What becomes more important is intellectual property. Now keep in mind, intellectual property is a commercial concept. Intellectual property is not a concept that gets along very well with open source. Open source is a technology that is a style that is just made for this technology. So there's going to be some tension there. We saw some previews of this in software patents. The US didn't have software patents until the mid-'80s. It did just fine for several decades without them. Now it has them, and most people are complaining bitterly, and a few people are extorting money, and I haven't seen they've done any good. Europe is still resisting software patents. Napster. When bits got too cheap to meter, people started sending bits arranged as songs. And there wasn't too much reason to pay for them. It took a while for the commercial systems to catch up, and they're still kind of fighting a losing battle, trying to instill fear in potential copiers rather than actually giving them an incentive not to copy. Okay, the cost to manufacture, for example, a computer could be 3 to 6 orders of magnitude lower than the value of that computer. This laptop, as I said, could be built for a small fraction of a penny. Obviously, it's worth today several $100s to me. Even more mundane products, this laser pointer, is worth maybe $10 to me, but I could build it for what? A hundredth of a penny, maybe a tenth. Black market, we will have one, unless we have, oppression and a police infrastructure orders of magnitude more stringent than the drug war to try to stop it. I'm not sure it can be stopped without basically everyone being owned and puppeted. If we're allowed to have nanofactories, we can have small-scale self-sufficiency. Cost of living may go way down. On the other hand, it may not, because all the new products like the direct neural interfaces, when those eventually come along, we'll probably have licensing fees and networks that can only be leased rather than copied to keep the price up. Productivity will go way up, which actually leads me to a concern. Today, people are very valuable working in factories. They can produce a whole lot of value working in factories, and that makes people very valuable. When, on the other hand, 1,000 or 10,000 people worldwide can do all the manufacturing that needs to be done, then does that mean that people's value will go back down? Does that mean that the Enlightenment values that came into being more or less along with the Industrial Revolution will start to fade away? Good question. Okay, how much will wealth concentrate? If the rich-poor divide was only, say, 1,000 times what it is today, then the poor could be very well off by today's standards if this technology is used to the extent that it could be. However, if the rich-poor divide is, say, 1 billion times what it is today, which is conceivable, then the poor could be poorly off by today's standards, could be even worse off than they are today. I don't see a whole lot of trends that encourage me to think that the rich will go out of their way to keep the rich-poor divide at a reasonable level. Okay, humanitarian issues. Cheap sensors and supercomputers mean you get communications, which increases accountability. This is a good thing. Means you get surveillance, which is a mixed blessing. It reduces crime, but it also reduces freedom. Cheap infrastructure creation. This is a very good anti-poverty measure. If you can go into a nation even that has no modern industrial capacity, and you give them a nano factory and a chemical processing plant and a batch of solar cells, then it can bootstrap itself in a few weeks, maybe a few months, until you have a nationwide manufacturing capability that's more or less modern, postmodern. That is if it's allowed. As I've implied and even stated, the powerful technology will definitely inspire powerful restrictions. This freedom versus security is, of course, a false dichotomy, but it is a dichotomy that we hear a lot about. One other big question, will people have a right to advanced medical care? Leon Kass, for example, says that we shouldn't have medical care that's too advanced. We shouldn't live too long. I'm not a fan of Leon Kass, but he has the ear of some fairly high people. Back to medicine, massively parallel sensors. I covered most of this. Let me just stress cell-sized probes and surgical robots. A bacterium is about 100 nanometers. A human cell is about 100 times that wide, 1,000,000 times the volume. And we know that you can build robotics based on biology in the volume of a bacterium because that's what a bacterium is. So Also, there have been some engineering studies that show a diamondoid robot arm with 6 degrees of freedom can be built in about 100 nanometers. This implies a surgical robot with a complete sensor suite and fairly sophisticated actuation in something the size of an acupuncture needle. Talk about non-invasive surgery. I covered rapid medical R&D and explicitly no more clinical trials. I do not know whether the US medical system can cope with this or whether we will see our lunch eaten by countries that will be better able to get away from clinical trials than we will. Neural connections become a definite possibility. We don't yet know what you can do with neural connections, but it has already been done that a monkey has moved a robot arm via neural connections. And I believe even via cerebral neural connections, it thought about moving it and the arm moved. Genome manipulation is likely. Augmentation, again, it's the people versus Leon Kass. How much will we be allowed to do? How much will we want to do? Is there a point beyond which it's not a good idea to do more? I leave that to you. I think Leon Kass is not correct about where that point is. I don't know if there is such a point. This may go to the runaway tech risk that I talked about a while ago. Okay, things that we will be able to do that we can't do today at all. We'll be able to get resources from space economically. We'll be able to move into space. The cost of going to space will actually be considerably less than the environmental footprint of staying on Earth. So what is not true today, if we do start to overcrowd the planet, we'll be able to move people off planet and actually improve the situation. Space obviously opens up new military and security concerns, space-based weapons and so on. Artificial intelligence and intelligence augmentation, that's what this alphabet soup is. Transhumanism, I just alluded to. Moore's law says that if you can build a computer that can read a book in 2.5 hours, and input that information, boil it down into a form that the computer can use, then in 1 decade, that computer will be able to read the book in 1 second. This gives some idea of how rapidly computers could advance once they get to a level of sophistication and competence where they can do things that we don't fully engineer into them in the first place. The observation, by the way, I owe to Josh Hall, who's writing a book on AI. Things we haven't thought of yet. There will be some. Possibly quantum computers will open up new opportunities for inventing things. Possibly new forms of chemistry that go beyond what I'm talking about here. Policing and criminology, I've alluded to this many times throughout the talk. I will say that commercial levels of product security are not nearly good enough. The DVD has been cracked. Basically, there are very few ebooks have been cracked, very few things out there commercially produced that have not been cracked, including operating systems, both commercial and open source, although commercial software seems even worse than open source. Lack of accountability. If you can build a weapon that's basically automated and that can be small and you leave it and maybe it travels under its own power, it could be considerably worse than landmines are today. It may not be possible to tell who deployed that weapon, and the weapon may be able to target people that you want to target. So this is just a hint at one category of very dangerous weapons and some of the problems that those weapons can produce. The only way that an armed society is a polite society is if people are accountable for their use of the arms. Otherwise, it's state of nature, nasty, brutish, and short. Obviously, as we've learned, attacks can go cross-border, which gets back to the question of policing other nations, which currently appears to be an impossibility. Humans are fragile and human institutions are fragile. It may be that, that weapon systems, not cockroaches, will be the last thing that survives. Okay, bad policies will not cancel out. Bad policies will feed on each other and make the problem worse, thus tempting more bad policies. Eventually that leads to panic, and panicked policy is definitely bad policy. There are no simple solutions. We have to find solutions in advance. I covered this. The security, the commerce, and the abundance are three very different kinds of issue that we will have to balance, and probably no single organization will be capable of doing that. This balancing act will have to happen on many scales, everything from what can the Nano Factory on your kitchen counter do, all the way up to what can the US military machine versus, whatever enemy of the weak military machine can do. The internet is a sneak preview of these problems. We have various kinds of nasty programs on the internet. Now, imagine those nasty programs, analogs of them in the physical world. Spyware that watches you type your password. Worms that eat your house for fun. Termites, of course, are very inefficient. Geopolitics and peace. Less need for foreign resources when you can build things out of light elements. Well, that sounds nice, except that it reduces international trade, which reduces one of the main incentives not to go to war. Better self-sufficiency is good. Less economic pressure is good. If people aren't feeling economically desperate, they have less incentive to go to war, but also less incentive not to. Very rapid development and deployment of weapons. If you can rapid prototype an airplane, if rather than a test taking 3 months and $3 million, imagine if it took 3 hours and $3,000 to test a new airplane, a new propulsion concept, a new spacecraft, a new type of gun. We could see very, very rapid development of weapons. We'll also see dual-use technologies. The same technology that allows your cell phone to understand what you say may allow spyware to understand what you say, et cetera, et cetera, et cetera. And the problem with dual-use technologies is it makes it very hard to regulate them, very hard to keep the lid on them. Do we need a global administration? Looks like yes. Can a global administration work? We have no clue how to make such a thing work. Again, we do not know how to avoid devastating problems. And when I say we, I don't mean CRN, I mean the whole world, including CRN. Recognizing the impact of molecular manufacturing on each of these problems, because they're interconnected, will be necessary for understanding how to plan policy for any of them. This is very, very difficult. The alternative is to accept drastic change that we can neither predict nor control. Thank you.